Okay, so we're going to do problem A from chapter 8. A 1.5 kilograms snowball is fired from the cliff. That's 12.5 meters high. The snowball's initial velocity is 14 meters per second, directly 41 degrees above the horizontal. How much work is done on the snowball by the gravitational force during its flight to the flat ground below the cliffs? So you want to find the work done by gravity. Okay, and you're asked to find the change in the gravitational potential energy of the snowball Earth system during the flight. So what is the change in gravitational potential energy? So you want to calculate delta U, that's due to gravitation. And the last part is that if the gravitational potential energy is taken to be zero at the height of the cliff, what is the value when the snowball reaches the ground? So in other words, this is where the snowball is located. We define this as initial, and so initial, gravitational potential energy is defined to be zero here. You also find when they reach at the ground, what is the gravitational potential right there? Okay, so what is UF? So when we do this kind of problem, you have this snowball that's going, that's being thrown from this point to that point, so it traces out projectile motion, and so you can see that the motion consists of two directions. One is in the horizontal and one is in the vertical. And you're asked to find the work done by gravitational force. Gravitational force only exists in the vertical direction. So the horizontal displacement has nothing to do with the vertical displacement. So by definition, the work done by gravitational force, Wg, is equal to gravitational force, the scalar product of gravitational force and the displacement. And that displacement is a vertical displacement. So let me just say d, and okay, so the vertical displacement. So gravitational force is in the downward direction, and the snowball is going down as well. So the displacement is, they are in the same direction. So when you do a scalar product, you can just use Fg, and then the vertical displacement, and then just leave it at that because they are in the same direction. The angle between them, cosine 0, is 1. So gravitational force, that would just be mg, and your displacement, the displacement here is your h, so you just mgh. So you have 1.5 times 9.I and then times 12.5, so that the work done by gravitational force is equal to 183.75 joules. Okay, so that's the work done by gravitational force. Now the second part is that what is the change in gravitational potential energy? By definition, again, we know that the change in potential energy is equal to the negative work done by the force. This is by definition. So and it applies to different kinds of forces. So in this particular instance, it applies to the gravitational force. So you have the work done by gravitational force, that the change is equal to the negative of the work done by gravitational force is equal to the change in gravitational potential energy. So in that case, what we have here is that whatever you calculate it and put a negative sign in front of it, that gives you the change in gravitational potential energy. So that's just negative 183.75 joules. Okay? So you can see that it's actually very straightforward and just directly based on the definition. So you don't want to overanalyze this. This is the basic principle. Okay? Now, the last part is that if this is taken to be zero, if we define, remember, gravitational potential energy is always in reference speaking, so you have to have a reference point. So at this point, in the problem, it says that if we define this gravitational potential energy to be zero at the initial height, what will be the gravitational potential energy at that location? So we already had the change in gravitational energy that has this main tube, and the change in gravitational potential energy always is equal to the final gravitational potential energy minus initial gravitational potential energy, and that's equal to this value. So it's equal to negative 183.75 joules. And because we define this to be zero, which means that the gravitational potential energy at the ground is just negative of that value at this position. And that makes sense because anything below the 0 point has to be negative, so that, if this is 0, then what's below that has to be negative. So the final answer is that negative 183.75 joules. Okay? So that's problem 8. And the next one we want to do is problem 19. So let me just erase this. All right, 19. Let's see. The diagram. So this is the diagram. We have this. We have stone. All right. So in this figure, it shows that 8 kilogram stone at rest on the spring. Okay. So the mass is 8 kilogram, and the spring is compressed 10 centimeters down by the stone. So when the stone is rest on the spring, the spring has already been compressed by 10 centimeters, and that is because the stone comes with weight. So when it rests on the spring, it's going to bring it down. So the displacement here is already, let me just say that it's 10 centimeters. Okay, and so based on this information, you asked to find the spring constant. So what is your K value? And then you ask, this stone is pushed down an additional 30 centimeters and released. What is the elastic potential energy of the compressed spring just before that release? So in other words, if externally it is being compressed another additional 30 centimeters, which means that the net displacement now is 30 plus 10. So it's 40 centimeters when it is being pushed down. And you also find the elastic potential energy. So you also find US. Okay. So what is the elastic potential energy of the compressed spring? And what is the change in gravitational potential energy of the stone system when the stone moves from the release point to its highest point? So you'll also find what is the change in gravitational potential energy. And then lastly, you'll also find the maximum height measured from the release point. Okay? So this is a diagram. You have a stone initially placed on the spring, and then because of the weight of the stone, so this is the spring has been compressed by 10 centimeters. Based on this information, we know that by Hooke's law, we know F, the force acting on the spring, is equal to, with the magnitude, is equal to Kx. So I'm just going to drop the negative sign because F is equal to negative Ks. So the force magnitude is equal to the spring constant times the displacement. And that must be equal to the weight of the stone so that everything is balanced. In fact, if you draw a free body diagram, this will be gravity of the stone, and this is the spring force. Okay, so these two have to be balanced and pointing in the opposite direction. So in that case, the spring force is equal to spring constant times the displacement, and that's equal to the mg. And you have the mass is given, and you have your g. So your spring constant can easily calculate it based on this. So mass is 9.8, and then over the displacement. Based on this picture, the displacement is 0.1 meters. So your k value is equal to 784, and that's in newtons per meters. Okay, so that's basically the spring constant that you got based on the information you're given. And then you also find what is the spring potential energy when when you press it further 30 centimeters further down. So in other words, altogether there should be 40 centimeters of the distance that's been compressed by the stone, the weight of the stone, and also external force. And you also find the spring potential energy, and the spring potential energy is just equal to 1/2, and then spring constant, and then the displacement. So in that case, what we have here is that you have 1/2 and your k value, and then the displacement is 0.4. So you square it, and then you should get spring potential energy that is equal to 62.72 joules. Okay. So after you press it down, like altogether that's 40 centimeters, and you release it. Once you release it, this whole thing, the spring, the stone is going to, let's say, so the spring will reach its original height, okay, and then the stone is continue to move, and then you're asked to find what is the highest point in reference to the release point, okay? So what is the change, before you do that, you're also asked to find what is the change in spring potential energy. So what is the change in in gravitational potential energy? Now all this energy stored in the spring potential energy has to be converted to the gravitational potential energy. During this time, when it's being compressed, there's only let's say, and we define the gravitational potential energy to be 0 here. So the only energy that has a non-zero value will be the spring potential energy, which is this value. So it's the initial conditions that you have an initial spring potential energy, and you have no gravitational potential energy. And then when you release it, this whole thing is going to, the stone is going to move. So it counts with the kinetic energy. But once it reaches the highest point, the only form of energy that will be present will be the gravitational potential energy. That's how so because energy is conserved. So based on the conservation energy, whatever you have here has to be equal to whatever you have here. And what you have here will be in the form of gravitational potential energy. And because we already defined the gravitational potential energy, using this as a reference point, we take that to be 0. Then, then this value of the spring potential energy has to be equal to gravitational potential energy at this point. So in that case, initially you have spring potential energy, and when they reach the highest point, you only have the gravitational potential energy. So you have the change in gravitational potential energy. So in that case, that would just be 62.72 joules. Okay, so this is based on the conservation energy, spring potential energy, and then gravitational potential energy. We don't really care about what's going on here so long as there's no friction. If there's no friction, then what you have here has to be equal to what you have there. Okay. And once you have the gravitational potential energy, and we know that gravitational potential energy basically is just equal to the mass times g, and then times the highest point. So based on that, you can calculate what is the maximum height that it can reach, measuring from the release point. So we have 2 times, it's 8. So you have 8 times 9.8 and then times h. So from there, you can find out your h value. That will be 0.8 meters. Okay. So all this is based on the conservation of energy, and there are various forms of energy present in this particular case. You have the spring potential energy. You also have the gravitational potential energy at the initial state and the final state. There is kinetic energy in between, but kinetic energy eventually converted to the gravitational potential energy. Okay, so that just during the intermediate state, so it doesn't really go into the equation. Okay. All right, so next one we want to do is problem 36. All right, 36, let me draw the diagram first. All right, so two children are playing. This is problem 36. Two children are playing a game in which they try to hit a small box on the floor with a marble fired from a spring-loaded gun that's mounting on the table. So here's the spring gun, and you have the marble that's trying to hit the target located at that location. The target box is horizontal in distance 2.2 meters from the edge of the table. Bobby compresses the spring 1.1 centimeters, but the center of the marble falls 27 centimeters short of the center of the box. So Bobby tried to hit the box here, but it missed the target. So it has a distance right here, and that's 20 centimeters short of the target. So let me just label that as let's see, how do I label that? So we can label that as D1. So Bobby, that's called a D1. So D1, which is the spring displacement, which is 1.1 centimeters, and the horizontal distance, that's called a X1. So your X1 here, that is 2.2 meters minus 0.27 because it's 27 centimeters short. So that would be, do I have a value here? I don't have, so let's just leave it at that, okay? And so that's that. And now how far should run the compressor spring to score a direct hit? Assume that neither the spring nor the ball encounters friction in the gun. All right, so Rhonda, the second person, we call her D2. So what should the D2 be? How much she has to compress the spring so that the horizontal displacement that reach the target, which is the capital D. Okay, so in that case, how do we do this problem? Let's see. So you have a ball. So this ball is loaded. This ball has the when you compress the spring, it contains spring potential energy, and then that spring potential energy is propel the ball to trace out projectile motion. So whatever spring potential on the table, whatever potential energy that the spring has will transform in the form of transform to the will transfer to the ball. So the ball will have that energy, and the ball has energy so that it will going to fly over across the floor, across the sky. So that energy will be in the form of kinetic energy. So in other words, based on conservation energy, we know that the spring potential energy right here has to be transferred to this marble ball in the form of kinetic energy. So let's do that. So let's say the spring potential energy is 1/2 by the first person is 1/2 K, and then D1, that's a spring displacement, and it has to be equal to 1/2 mass of the marble ball and then the velocity of the marble ball. Okay, so you have 1/2 KD1 squared, that's equal to 1/2 MV1 squared. You can see that we're not giving a lot of numbers here. We're just going to use a simple for now. Now, for the second person, and then D1, of course, is given. For the second person, she compressed the spring, that's say D2. So you have the spring will have a potential energy that's 1/2 K D2 squared. And that has to be equal to 1/2 the mass of the marble and then the velocity of the marble. Okay? So in that case, we have all this. What we can do is that we can just take the ratio, and then all the common factor, they just get canceled. So what you have here is that you have your D1, the spring displacement, squared, over D2 squared. That's equal to V1 squared and then V2 squared. Okay? This equation, the only information that we have is your D1. D1 is given. D2 is the one that you asked to find. We don't know V1. We don't know V2. So what's next? So what's next? Okay. So what we're going to do is that we're given the horizontal information. So we're going to use that. Now, if you look at this diagram, so you have this is the trajectory traced by the marble ball, and then from the first person, and this from the second person. So you can I'm sorry, I had it reversed. The first one did not hit the target, and the second one, this is with the aim that she's going to hit the target. So in that case, this is the horizontal distance. This is your x1, and this is your x2. So in that case, we have the velocity, and because it's the ball is actually moving in this direction, which means that it only has initial velocity in the horizontal direction. There's no vertical velocity. So and then it's going to fall under its own gravity. So it's going to trace out the trajectory like that. So in that case, we can use the equations of motion just to see utilize the information of what we're given. So what we have here is that if you take this initial point to be 0, then the displacement, the horizontal displacement for x1 would just be velocity v1 and then times time. Because we're dealing with the horizontal motion. There's no vertical velocity. There's no vertical acceleration. So you have the horizontal displacement is equal to the initial horizontal velocity times time. Okay. Likewise, your x2, which is this distance, is equal to v2 and then times time. Okay, so your x1 is given, and your x2 is also given. So from there, you can actually find out what the ratio of the velocity is, and then we can plug into this equation. Okay, so you might say, okay, wait, how do I know that the time is the same? Because in order to do that, your time here has to be the same. Now, if you look at this, in the vertical direction, because this is trajectory of projectile motion, it has a horizontal distance, it also has the vertical distance. That vertical distance, let's say, is h. This marble ball, during the first trial, during the second trial, it all moved the same vertical distance. If you recall, the displacement, yf, final position, is equal to initial position plus initial velocity in the vertical direction times time, and then minus 1/2, and then gt squared. So in that case, the displacement for trial 1 for your h is equal to, and there's no initial velocity, so you only have 1/2 gt1 squared. That's say for h1, and your h2 during the second trial is negative 1/2 gt2 squared. So you can see that because h1 and h2, they move in the same vertical direction, which means that your t1 has to be equal to t2. So that's why they travel in the same amount of time, okay? Even though the horizontal distance, horizontal distance are different, but vertical distance is the same. So which means that it takes the same amount of time for them to reach the ground. So you have the x1 that's equal to v1t, and then x2 that's equal to v2t. So you take the ratio, and your t just get canceled, which means that your v1, this is equal to v1 and v2. So we're going to go back here, because your v1, the ratio of v1 to v2 is equal to the ratio of x1 over x2. So you can actually just use that, and you have square. So now we're ready to plug into the information we're given. Your d1 is 1.1 centimeters. We're just going to keep that, so that after you do the calculation, your d2 will also in centimeters. So you have 1.1 squared, and then d2 squared. That's equal to x1 over x1 squared over x2 squared. Your x1 is 2.2 minus 0.27. You square it. And your x2 is just d, which is 2.2 squared. So after you do the calculation, your d2 is equal to 1.25 centimeters. So this is the amount of the this is the amount of displacement that has to be that has to compress the spring so that it will hit the target located at this at this point. Okay. So basically, that's that. All right.